Winfried Mayr, the person who will be giving the talk, is an expert in FPS, functional electrical stimulation. He's in Vienna.
Yeah, then good morning, everybody. Thanks for inviting me, and I'm very unhappy that conditions were like that I couldn't come. I would love to be with you, but so we use modern technology to do our communication remotely. I hope we have some time at the end for discussion, which I would very much appreciate. So my background is an engineering one. I'm in the Vienna Medical University in a technical facility that is quite unusual to be embedded in a university clinicum, but we have the mission to support research all in the house, and also we have focuses on cardiovascular engineering, and in my field it's more neuroprosthetics, implants, electrical stimulation since quite a long time, but we are able to manufacture prototypes and apply it in the clinical setup, but also in animal experiments. Yeah, today I want to share some thoughts on the critical issues of electrical stimulation. So I don't want to discourage anybody, but I want to make somehow a little contribution to informed awareness that electrical stimulation is not just stimulating a nerve and using the immediate muscle reaction, but there are more things to consider, which are more possibilities, but are also limitations. So we have a huge number of different stimulation equipment on the market. Most of you will work with part of this, and this is just a few examples to categorize this. So we have general purpose stimulators in the upper row that can be used for various therapeutic and neuromodulation applications. Then we have dedicated equipment, non-invasive dedicated equipment in the middle for the arm, for the legs. Not much is on the market, but there is something. And then in the lowest row we see implanted solutions that are, of course, a little less available. And on the left, I have just as an example the freehand system for the upper extremity. But this has disappeared, unfortunately, and we have quite some so-called general purpose implants left that we can use for various treatments, and that have the advantage that they are somehow affordable and constant on the market. Over the years, a lot of fancy technical equipment, technical solutions have been developed, and the new opportunities of IT technologies, of course, give us much more flexibility in constructing good solutions, but there is one bottleneck that remained nearly unchanged over the years, and this is the interface between the organism on one hand, which is an ion conductor, and the technical conductor, various types of electrodes. And this has always been a very critical part regarding safety and regarding limitations in selectivity of what we want to excite in the body, neurons, muscle fibers. I have just a few examples here, especially two extremes. So on the lower right we see an array of electrodes that is meant for retina implants. And as you see, the resolution of this potential image is very low. And this is not because it's not possible to make arrays with more poles on the same size and smaller dots, but there's a real limitation on what we can deliver across the electrode safely and to have still an efficient stimulus. So if we make them smaller, it gets either difficult to deliver a stimulus that is already enough to elicit action potentials. On the other hand, if we overload these tiny contacts, then we get corrosion and tissue damage. So we are really on a border, and now since many years that inhibits the progress. On the other end, the upper left, there are electrodes for muscle stimulation of big muscles, quadriceps muscle, for example, and this is for direct eliciting of action potential at a muscle fiber in absence of the nerve, and there we need much higher charge transfer across this critical interface, and we have then problems of skin damage, for example. So in between there are many solutions, so non-invasive, invasive ones. On the upper right we have one type of electrodes for epidural stimulation, for spinal cord stimulation. In the middle we have the Vienna epineural electrode that is used for quite some time in the clinics and has a small loop with a diameter of about 0.8 millimeter. The nerve is from upper left to lower right. And also in the neuromuscular nerve stimulation, we come to these borders when we have electrodes in the size of about 1 centimeter square, which we have on the lower left for selective spinal cord or posterior root stimulation. So this is just indicating what I mean with this somehow danger of tissue damage, electrode damage. I have written here no DC. There are exceptions. It's also quite fashionable to use DC stimulation at the moment, but there is a high risk that is often disregarded, and the low DC can be nicely used to influence motor control, neuromodulate certain spots in the spinal cord or in the brain. But on the other hand, we always need to be careful. There are also studies where the same current in the same highs or amplitude is used for damaging neurons. For example, was one idea to substitute Botox by this, and this also works. So there's always some care necessary when we use DCs. If we have charged balanced impulses, we have no unlimited range to deliver impulses. We have a charge injection limit that we need to respect, which is the amplitude versus impulse length, and the limit is defined by the material and by the size of the electrode, and if we exceed the charge injection limit, then we get irreversible changes in this critical interface from electron conductance to ion conductance, electrochemical processes that damage the tissue and the electrodes. Yeah, this is a very nice example that shows us how we recruit. This is a group in Liverpool, Jonathan Jarvis, Stefan Eickhoff. They have a nice red setup where they stimulate a nerve directly with tiny spot electrodes, and immediately after this site they are able to record the action potentials from the nerve, which is tricky and not easy. And in addition, they can also do isometric force measurement on the connected muscles. What we see very nicely here, they use extra long impulses. The reason is just that the stimulation artifact makes problems in recording these tiny ENGs. And with this prolonged impulse, which doesn't change too much from the recruitment, but which is somehow in the Rao base of this time amplitude threshold curve. There we are in the Rao base, and so it doesn't change if we have 1 millisecond or 5. But the advantage is that we have a roof of these recordings where we see also the ENG, not only the stimulus artifact. We have a range where we are below threshold. Then we see that the longest edge, like expected, elicits some action potential on top. Sorry, I forgot. I cannot point, so I need to describe it. Yes. Then in the next step, we see that there's a co-recruitment of the negative edge of the pulse. It is known that a negative edge has a lower threshold than a positive edge in principle. And if we go further up with the intensity, then we come to the third recruitment portion, which is on the positive leading edge. So this makes us aware how we recruit. We also see in the fourth recordings that there is a saturation, and the saturation means that we cannot recruit additional neurons, but on the other hand, we start with higher intensity to hyperpolarize the early recruited neurons and get a block of this to develop action potentials. Another thought I want to share is what we have in the mixed nerve. So we, in general, are used to stimulate a motor nerve and get the reaction. But if we have a closer look to the amount of motor fibers in a nerve compared to the amount of afferent fibers, of sensory fibers, then we see that there is a huge number of afferent nerves that are to a high percentage bigger and more excitable than the motor nerves that we always co-activate when we do neuromuscular stimulation. And there are effects that we have seen in the past that were not so easy to explain, but in the meantime there's a big tendency to foster afferent nerve stimulation, because we have learned that a lot can be done with afferent stimulation. A lot of beneficial effects can be accomplished with this type of sensory stimulation, but we need to know what we do exactly when we apply a relatively coarse tool. When we have a closer look to the nerve, on the left side we see a sensory nerve, and we see the distribution of these A fibers, which start roughly with 20 microns in diameter, are grouped in a Gaussian characteristic, the different defined types, and we have the largest number towards 1 or 2 microns of C fibers, of pain fibers. So this is all mixed up in a small nerve of about 1/4 of a millimeter diameter. If we look on the motor nerve on the right, we see that the lower motor neuron, the cell that is responsible for the neurofibers, lies in the interneural network of the gray matter in the spinal cord, and then conduct again in a mixed way and with different diameters to groups of muscle fibers, so-called motor unit. And these muscle fibers are again intermixed. So we are far from selective access to single muscle fibers, let's say, control of single muscle fibers. Next slide. Yeah, I have indicated here the size relation, the same sensory nerve, and then a drawn 1 millimeter nerve against an electrode that is 0.5 millimeter in diameter, close to the epineurium. We shouldn't go closer due to biological reasons. And then we have different sample neurons. There are 2 simple rules that help us to estimate what we recruit, and one rule is that the threshold is inversely proportional with the size of a neuron. Big neurons have the lowest threshold to be recruited, and then the distance plays a certain role, which is not so big in the small dimension of a nerve and a close electrode, but plays, of course, a role. This is the distance relation. The square of the distance decides upon the threshold of the stimulation in the same field. Yeah, this is a nice illustration I got from a book which shows the conduction speed of fibers, and conduction speed is directly proportional to the threshold in an artificial electrical field, because the speed is higher when the membrane around the neuron is more sensitive. And we have this plotted against the size of the fibers, and we have the efferent and the afferent fibers, the motor and the sensory nerves. And what we see here is that the biggest fibers we have and the most sensitive fibers we have are afferent fibers, the proprioceptive fibers that give us information on the body image. And then we have cutaneous fibers and with declining size and sensitivity, also pain fibers. On the other hand, we have the efferent motor fibers with the well-known inverse recruitment that is associated with most applications of FES. The large motor fibers supply quick fatiguing, strong muscle fibers, and when we stimulate with higher intensities, we also reach the endurance fibers with type 2 metabolism, and of course the nature does it the other way around. This is an example when we consider to stimulate the posterior roots, the sensory roots in the back of the spinal cord, with non-invasive means, which is often published these days, and we see a small electrode in the back near the lumbar cord, and we have a big electrode on the abdomen. And this should just give an estimation what we reach when we want to induce sufficient stimuli to the posterior roots. And we see that predominantly first we stimulate the dermatomes below the electrodes on the belly and in the back, and we first reach the sensory nerves in the skin, then we reach the motor nerve and provide inputs on a higher level in the spinal cord, which is not intended for a defined stimulation. So we have inputs between TH6 and TH12, whereas our target is TH12 and TH11, where we want to have the origin of the lower limb nerves, and there we have the same problem of recruitment. We have first the recruitment of the large afferents, and then with growing intensity we get co-recruitment of the smaller ones. If we try the same thing with epidural stimulation, electrode directly at the dura, closer to the spinal cord, the main advantage is that the external co-stimulation is vanished, but we still need to consider the recruitment order in order to interpret what we see. And just one example why this matters. Again, on top in A, we have this proprioceptive afferents, the body image coming from muscle lengths. In this case, they are more, of course, relevant for having a full image. But these are the only neurons we can somehow stimulate selectively, because they have the lowest threshold and they have a very simple safety reflex reaction, which is monosynaptic and quick and has an inhibitory component with reciprocal inhibition and the excitatory to activate the muscle on the reflex pathway. If we just go a little higher with the intensity, then the A still is stimulated, but the B is co-recruited, and there we have cutaneous afferents in different sizes. And what this slide should tell us, the processing gets much more complex in this case. So we have, of course, unphysiologically not a selective stimulation of these lower processes, but we have a co-recruitment, and there we have an implementation of a processing that includes the contralateral side and the ipsilateral side, just to give some impression to be aware of this. Historically, it is not so long that we know about this processing capacity. Roughly 1850, it was only seen that nerves, that there are motor and sensory nerves, afferent nerves, and it took 60 more years till the first monosynaptic reflexes were discovered. But then Lundberg made a very good discovery, a very important discovery for contemporary applications, which are the premotor centers in the interneural networks. And this shows us that we need in these premotor sensors a certain state of excitability, we call it, where we get inputs from afferent nerves in the periphery. We get additional inputs from descending pathways in the spinal cord, and there must be a critical excitation level to send away an action potential to the motor nerve. Very often we miss descending pathways, and then the central state of excitability is not high enough to execute a movement, and sometimes there can be help from an artificial stimulated input, even so it comes through wrong neurons, but then we can exceed this level, and then we can execute movements that are not possible as long as we don't support it. And there's a famous discovery on the right side, the CPG. I think the CPG is of course an interesting modality, but in the meantime we don't anymore expect that we just stimulate with the appropriate frequency and have a cyclic movement like we can do in quiet conditions, but we have learned that the generator is only part of the control system. It doesn't work if we don't have appropriate feedback and if we don't have appropriate descending control. On the side of engineers and clinicians, the story of neuroprosthesis began more or less in mid-past century when the transistor was invented and when it was possible to design portable battery-powered equipment and implants. So all of our neuroprostheses more or less have their roots at that time, because physiological knowledge was already there and technical means occurred. But the engineers and clinicians disregarded very long the findings in the neuroscience above. In spinal cord injury, it is often forgotten that immediately after the accident, at least, we have totally intact structures, neurological structures and muscle structures below the lesion, and the damage is just in the injury zone and in the descending and ascending system in the spine. It would be valuable to start early with the stimulation. The best would be immediately after the surgery, because it's neuroprotective and we can maintain what is there and hope for recovery. In the current primary rehabilitation, this is very seldomly the case, and a lot is already lost when we just suppress spasticity with medication and have no electrical activation during at least the first half year. But I think that there's a tendency to change this. On the other side, on the right side, we see the system that we can stimulate. We have the spinal cord nicely in the cross section with the gray matter in the middle that does all the processing. We have the white matter with ascending and descending pathways to the brain, but also to other areas in the spinal cord, which is also often underestimated. There's a big role of the trunk muscle coordination with the leg muscle coordination. Without this, it's very difficult to execute proper movements, and so there are a lot of signal exchanges already in the spinal level that might be altered or inhibited. Yeah, this is this should show you where we are over time with restoration of walk, which I think is a long story, and the level has somehow saturated to some extent. We have now 50-60 years of work on this, and the lower three videos are from the 1990s. The upper two, the most actual and spectacular videos from the group in Lausanne. But overall, it is in all cases we have a very nice therapeutic walk. It has high value to verticalize people, to keep the neuromuscular system activated, and I think this is per se already a very big value. But it is not a restoration of gait like it is often promised. I'm sure you are all aware with the classification of the Asia scale, so I don't need to repeat this. But we have in the lower three cases we have Asia A candidates, complete sensory and motor lesion. In the upper scale we have Asia D, which is incomplete. In the lower scale we have surface electrodes involved. In the upper scale we have an implant for epidural stimulation, and the most special patient is in the middle at the bottom. This lady has denervated lower extremities, so she doesn't use neuromuscular stimulation, but she has muscular stimulation because the nerves have disappeared. So over time we have here in Vienna worked on various types of electrical stimulation, and internationally many groups have done the same. There was a tendency in the 1980s where I was a young assistant in our group. We started with implants and had a 4-year project with 4 patients with multi-channel implants to activate leg functions. There was also an early bike, as you might see. And very soon it turned out that this is totally unrealistic. First, there was a lot of effort put into closed loop and multi-channel stimulation, but it turned out that this is much more difficult than expected and never payable for any health insurance. So it disappeared, and most or nearly all groups moved to the cheaper and simpler surface methods. On the bottom, on the lower left, you see an application of the same implant for phrenic pacing. This was a successful application, so we had in research, we had about 25 persons supplied with a lesion in the very top of the spinal cord, C1, C2, with loss of respiration and all movement functions. And we still have patients from that time that live with this implant, and there's a company in Finland that also supplies with implants. So this is a very good solution for very few patients, fortunately. And in this respect, an implant is the only solution, of course. But for walking, it was too expensive for the effect. We have then worked for years with this neuromuscular gait support in 6 channels, so quadriceps for knee extension, gluteus for hip extension, and then peroneal reflex for the gait cycle, like everybody does. Then we have had a big project on muscular stimulation, which is quite important because 1/3 of the paraplegics have problems with denervations. And now, like everybody, we have also learned that spinal cord stimulation and afferent nerve stimulation on different locations is very powerful. This doesn't mean that the art has developed in this direction and the best solution is the last one, but I think all of the solutions that are displayed here need to be taken together to find individual solutions for patients, because the needs of the individuum is unique. The spinal cord injury is like a fingerprint, and we need to do proper assessment and then plan and combine our abilities to support in the best way. This is just, if you are not aware of this, what is available for spinal cord stimulation. For a very long time, it was a simple system on the lower left from Embryonic with just 4 channels and very limited controllability. On the right side, we see now that there are several providers with multi-channel systems with a very good standard of different electrodes, of parameter variation, and so on. Yeah, what we do now mainly, we use non-invasive techniques for assessment of spinal cord injury. And as already said, we need to find out what the individual profile is, first for planning an intervention and then monitoring the intervention to come and also correct it when necessary, to see where we have recovery, where we have adverse effects, and how we can come to an optimal solution for the individual patient. Normally we do this in supine position, but for incomplete patients we sometimes do it in upright position, because the influence of the vestibular system and of the posture muscles is quite high. In this example, we just have a gain curve from threshold to saturation of the monosynaptic reflexes in all 4 main muscle groups in the lower extremities. And we plot them, but this is only one of many tests. It lasts about 3 hours, and we have passive tests and we have tests with stimulation. In general, when we do this simple spinal cord stimulation, which is normally a continuous tonic stimulation with no phasic on-offs, but just constant amplitude, constant frequency, then we already see that the output can be very different. Again, we plot here quadriceps, hamstrings, tibialis anterior, and triceps surae group, left, right, and then we see in some patients we have tonic output, in some patients we have phasic output that is even coordinated between flexion and extension, and in some we have mixed results, like on the lower left, and sometimes we have complete suppression. On the upper right, you see that normally, or very, very often, we see a decline of the reflex reaction. This is one reaction per impulse that we have plotted here, and with higher frequency we get more inhibitory effects, but this is not a general rule. This is seen often, but not always, and sometimes we have inhibitory effects already with 20 Hz. This should just show, this is one example of a passive multi-joint movement of the leg, and we see that there is a constant stimulation and just a slight shift in the frequency from 10 to 16 Hz. And you can see how much this already influences the pattern of the output, of the reflex output. So we see that the processing in the spinal cord is very strongly frequency dependent. And this is a very interesting and nice example. This shows when we have a complete spinal cord injury, we can test something between complete and incomplete that we call Discomplete, and we see this when there is a residual conductivity across the lesion. In black you see reflex reactions when the patient is totally relaxed and does no influence attempt of his movement, and in red we see if the same stimulation is done in the same setup and the patient is asked to try an extension of both legs. So you see that despite he cannot execute any movement, he is able to influence this reflex pattern, and this tells us there is a residual connectivity and we can try to make something out of it. And this is also an example from this from this assessment test, the Babinski reflex, a mechanical stimulus at the foot sole. We saw without stimulation, we see a strong withdrawal, in this case in the left leg. The right leg is much less excitable. We often have these asymmetries. When we stimulate with the 20 Hertz and with 10 Hertz and 20 milliampere, we see that the reflex is even enforced, so it is facilitated. But if we stimulate with 50 Hertz in this case and 40 milliamps, then we see the reflex gets totally silent. So we get some option to control this type of reaction, which is closely associated to spasticity. Yeah, we do this all. I cannot go into details with a computer system. We hope that it will continue to be a learning system to provide already processing of data in real time for the clinicians to collect data from other centers. But in essence, it's a computer system with two controlled stimulation outputs and 16 controlled EMG inputs, and this can somehow manage protocols in a very repeatable way and collect the data and make them comparable. Yeah, this is one example on the therapeutic effect of this type of stimulation. We have a pendulum test that is quantifying the spasticity. Spasticity is attention speed dependent reaction. In the pendulum test, we just release the leg, the extended leg, and let it swing down. We record EMGs and the knee angle, and in the upper example we see that there's a huge reaction in different muscle groups that stops the swing very quickly. If we do stimulation with the tonic stimulation with the appropriate frequency, then we see that we have silent muscles and have a nice sine pendulum swing with an exponential decay like it should be. So, yeah, we can do similar things in gait support. So this is an example with a locomat. It could be similar with a bike, for example. And we see that the mechanical stimulation already elicits some phasic reactions. These are mixed from different patients. The mechanical stimulus, the afferent input from this already elicits something. It can also elicit inhibition, spasticity reactions, clonus. But if we add this simple way of stimulation, then we can see that the reactions get much more pronounced and that the inhibition can get silent. And this is a way where we can proceed with gait training, and partly it could also be useful for FAS spiking. In this example, you see an HRT patient that is already able to do some gait with crutches, but only very limited and exhausting. And on the first side, you don't see much, but if you look closer, you see that the lifting of the forefoot is much more efficient, the ground clearance gets better. And for the patient, it's not spectacular, but it means that instead of a few meters, he can go for longer distances without getting exhausted. If I still have time, but you stop me, in case I want to come to the denervated muscles, which are more and more discovered. For a long time it was considered impossible to stimulate and maintain denervated muscles. In the meantime, we know better. The difference between nerve and muscle stimulation. The main difference is that we need much longer impulses for a denervated muscle, from a minimum of 50 milliseconds per phase. All other parameters are comparable with neuromuscular stimulation, but this, of course, causes safety issues and technical issues. Next slide. So a healthy muscle, if we look on the cross-section of the muscle, on the histology, and also on the electron microscopy inside the muscle, we see that there are nice organic structures that are highly functional. And I don't go on the details of this anatomy. We have this coupling from the spinal cord interneural networks to the synapses and the muscle fibers. If we now denervate a muscle or just shut it down by chemical means, for example, then we see that very rapidly we lose muscle and we get a substitution by connective tissue and fat. And you see already in the first year we see atrophy, which means more connective tissue, smaller muscle fibers. But in the second year it gets really dramatic. We get a damage of the interior of the muscle fiber, so we lose these nicely structured protein structures, and the organelles are damaged also. And in the histology we see a lot of fat and very small fibers in the biopsies. And if you look in the cross section of the thigh, you'll see also little is left of the muscle, embedded fat and connective tissue, and surrounding fat and connective tissue. You can imagine that a lot of long-term problems occur in this condition, and in the range of 10 years or so, it gets hopeless to do something on this. So this is just maybe it's a little bit short on time, but this just tells us that we can recruit satellite cells, which are the stem cells of a muscle fibers, and develop new muscle fibers by means of electrical stimulation, but also by means of mechanical stimulation. The green staining here tells us that there is embryonic myosin, which is only expressed a few days after development of a new fiber and then disappears again. This is what can be accomplished with stimulation. The earlier we begin, the better the results, and we have here indicated the different tissue content. There's one adverse example here on the upper right. This is a professional athlete, a cyclist, a woman that you saw in the video already, and she had unusual preservation of her muscle and unusual success in the training, even as when she started already as late as 3.2 years. all other patients need very much more time to come to a similar result. But a muscle that is used intensive training is obviously also reacting better on electrical stimulation. This is just, there's little time now to explain this, but this is plotting in a study with 20, this is a plotting of a study with 20 patients. We have different parameters plotted over the innervation time, and we have plotted them 2 years later with intensive electrical stimulation training. So we get bigger muscle mass, we get bigger fibers, we get bigger torque development in the knee in this case, and we have a nice linear relation between size and force development, which is essential to know that we have a healthy muscle even after 2 years of stimulation. Yeah, what is very essential regarding electrical stimulation is the muscle fiber conduction velocity, so the action potential that travel along a fiber are slower after the innervation. And with electrical stimulation, we can restore this. In this setup, we see it. We have a stimulation needle, we have a recording needle, and we can calculate the muscle fiber conduction velocity. And with a two impulse regime, we can also look on how fast a fiber area is recovering after developing an action potential, which also is prolonged in the degenerated muscle, but can be readjusted with the stimulation. Yes, this just tells us that within 1 year we can double the muscle fiber conduction velocity, which is essential, and also the recovery of the membrane around the muscle fiber. Yeah, a big problem of the stimulation of denervated muscles are the long impulses. In long-term denervation, we need even up to 500 milliseconds per phase to get a reaction. But very quickly we can condition the membrane, the density of ion channel is increasing and the kinetics is getting better. And so we start with single twitch training or conditioning of this membrane, because we have no other choice. We cannot get a fused functional contraction initially, but then very quickly we can go down with the necessary pulse width. And when we come in the range of 15 20 milliseconds per phase, then we get a fused contraction, because we can stimulate in the range of the fusion frequency for a fused contraction instead of shaking contraction or single twitches. There is an option to avoid co-activating of the nerves. So often patients with denervations have intact sensation, and these long impulses are not that pleasant during stimulation. So another cause is that we have motor nerves around in incomplete lesions, and we want selective stimulation of muscles. And these accommodating ramp-shape impulses are known quite long, that we have a range in the length where we have a lower threshold for the nerve than for the muscle. This is very helpful in mixed cases, which are frequent, where we want to do extra stimulation of innervated parts and of denervated parts. At the end, we come to this functional standing, functional stepping, big advantages in tissue conditions, skin, muscle, and avoidance of pressure sores. These injuries are, most of them are very early, so people have a long life expectancy and they have growing problems if they don't do anything about this. And this is very important to avoid pressure sores. On the other hand, if we can do standing up, which most of the patients accomplish sooner or later, then we have a loading on the bone, which is often underestimated. Young people have heavy osteoporosis below the lesion and associated bad healing and easy break. On the other hand, what's also very important is cardiovascular fitness. So our patients do 50-60 stand-up trials a day to get a better cardiovascular regulation. This is now at the end a little bridge to the biking. So we have a very nice collaboration with Josef Laschko in the rehab center in Budapest, and we have a bike there. It's not so easy to do pedaling with the innervated muscles because the flexion functions are very weak, but this rowing mode is quite helpful. So the chain is moved by the chair movements, so the patient can pull forward just in passive motion and then stimulate the quadriceps muscles completely asynchronously, very simple, and the chain is grabbed and pushes the bike in this way. So it's one option, and to my best knowledge, nobody has yet biked with the innervated muscles, but the patients like it a lot, and I think a lot of improvements could be done in this technique, and for us it's just the beginning. This is just to also mention that there are a lot more of very important applications that are underestimated now. If you see these severe denervations, plexus lesions, facial nerve lesions, laryngeal nerve lesions, there's a lot of potential of maintaining the innervated muscles as long as they are denervated, because in a plexus lesion you need to consider 2 or 3 years for reinnervation of an alternative nerve input, and in this period you lose all muscle, you need to do muscle transfers and so on, but if you do stimulation in time you can maintain muscle targets and get them preserved for a later reinnervation. In the face this is important, and also in the larynx it is important. This is one slide that I also want to promote due to my nice workplace here in the clinic. I think it's very important that engineers, physiologists and clinicians, including patients, talk to each other. I think it's only a more or less full or enhanced understanding given if engineers are supported by clinicians, if clinicians are supported by engineers, both have a different view of what the other can do. And physiology plays a big role, and we need to have qualified support to interpret what we see. This is on one hand when we start technical developments and bring it into clinic, but also in the other direction, that the idea comes from clinic and moves to engineering developments. Yeah, and this is just also one last thought. If we apply implants, and in the past this was done from time to time and got lost again, we need to be very careful what we do to the patients. I mentioned these general purpose implants for the spinal cord stimulation. They are very reliably available. There are big companies behind, and we can trust that they have lifelong technical support, more or less, for the patients. In smaller companies this is more difficult, but there are positive examples like the Brindley bladder stimulator or the Atrotic phrenic stimulator, but the majority of these implants is just implanted, and after this people think, how can we remove it without damage? And I think it's unethical to do it this way. We need, before we consider an implantation, not only have the financing for the implantation, but we need to make sure that there is lifelong support and there is an exit strategy that doesn't hurt the patient's integrity too much. This is just a thought that I want to bring when I look at the freehand system. For example, the company got bankrupt, 350 patients were left over. This is not possible. So we need to be very careful and have a good reason when we implant implants. Yeah, and this is my last slide. It's just part of the group and of the collaboration partners. Professor Dimitrievich is our big mentor who supported us a lot with implementation of the spinal cord stimulation. He's in Houston and 3-4 months usually in Vienna, but at the moment he's trapped in Houston due to known circumstances, and we have clinicians of various background and engineers of various background working together, which is very nice, as we are more or less in one building and have external collaborations. So then I thank you for your attention. I hope I didn't use too much time, but and I hope it was somehow interesting.
Thank you very much, Winfried. We will move to some questions. And I have a first question about the Innervated muscle stimulation. I understood that you need much more power and you're using much bigger electrodes, mainly for standing. I was wondering if it's possible and if it's of any interest to do the Innervated muscle stimulation of upper limbs.
Yes, this is a very important part. Thank you for the question. I mentioned that plexus lesions is a big potential for this, even though it's not established yet. But you can maintain muscles. All of you might know people that had a plexus injury and then very thin arms and even consider amputation. But I think there is a big potential for electrical stimulation to maintain the muscles they have, and then the neurosurgeons do their job, and then it could come to much better outcome of this surgery. The same is in the facial muscle damage, tumor resection, and so on. There is a long period where the muscles degenerate, and if we maintain them, they can be used for reinnervation targets later. But in the upper extremity, we also have patients here. We have an outpatient clinic for spinal cord injury, and we very often see that in the upper extremity we have mixed lesions with some voluntary control left, with some innervated paralyzed content and some denervated content, and it's very nice. You can train for example, the finger flexors with the parameters for denervated muscles. You can train the interossei to keep a cushioning in the hand with these long duration impulses, and in addition you can do neuromuscular stimulation of parts of the muscles. Very often we see that it is mixed, and then it depends upon the portion, how many motor units are still innervated, how many are denervated, and then we can decide, do we support the reinnervated, do we support the innervated part and train the innervated muscle content to give more functionality. On the other hand, we can train the denervated muscle fibers and hope for reinnervation processes. And so at the end, we should always have a close look on the individual patient and then try to maintain what he has and make the best out of it.
Thank you, Winfried. Sorry, I cut you.
Hand is a big topic also here, so we have many higher lesions, C5, C6, where this is a topic.
Thank you very much.
Hello, Winfried. This is Vance Bergeron from École Normale Supérieure speaking. I have a question. Yes. I have a question concerning interferential excitation using high frequencies and the beat frequency to and also amplitude modulated high frequency stimulation. Mm-hmm. Do you see advantages or disadvantages in using that type of stimulation, with the presumption that if you used high frequency, you could bypass some pain levels and then still with the beat frequency excite the muscle? Do you have any experience or any point of view on that?
This is, I think the effects are not totally different. There is some report that it's a little bit more comfortable because the skin sensation is less stimulated. The capacities of these skin layers, of these low conducting skin layers, bypass the current with the higher frequencies. But it's not a tremendous difference. At least it's something it's worth trying. It's of course more costly and less simple to handle, but it is one of the options we need to consider for certain cases. It's the same with magnetic stimulation. It's a little bit similar because also magnetic stimulation, functional magnetic stimulation gives an option where we nearly have no excitation of skin structures, but very good excitation in the depths, for example, for pelvic floor stimulation with intact skin sensation and such things. So it is, there are different modalities we can use, and the classical interferential current is of course nice if we have a rigid system. It's much less reliable if we have a movable organism where the focus point of the interfering currents is moving also, and then the advantages are lower than expected. So I think it's always worth trying if there are problems with sensation, hypersensibility and so on, but it is not a miracle difference.
Great, thank you very much.
Okay, I think we have no more questions. Thank you very much.
Thank you, bye-bye.
Goodbye.